Cohesion tells how closely the parts inside one module, like a class or a function, work together on the same idea. Imagine a toy box that only holds building blocks. All the blocks are used to build houses, so the box has high cohesion. If the same box also held crayons, a soccer ball, and a sandwich, the items are unrelated, and the box has low cohesion. Types of cohesion from weak to strong. Coincidental items are put together by chance, like a random pile of toys. Logical items are grouped because they belong to the same category, but they do different jobs. For example, a utility class that has many unrelated helper methods. Temporal items are together because they happen at the same time, like a setup routine that runs at program start. Procedural items are ordered to run one after another, like a recipe that tells you step by step, even if the steps are about different dishes. Communicational items use the same data, like a kitchen drawer that stores all the spatulas. Sequential one item's output becomes the next item's input, like a factory line. Functional everything in the module works on the same single purpose, like a flashlight that only turns on and off. Functional cohesion is the strongest and what we aim for. Coupling describes how much one module depends on another. Think of two friends sharing a secret. The more they need each other's secret to act, the tighter the coupling. If they can work alone and only talk occasionally, the coupling is loose. Types of coupling from loose to tight. Content/knowledge coupling. One module directly reads or changes the internal data of another, like peeking into a friend's diary. Common coupling. Modules share a global variable or file. They both use the same notebook. External coupling. Modules rely on the same external device or format, both using the same type of USB cable. Control coupling. One module passes a control flag to tell the other what to do, like telling a sibling to clean your room versus play. Stamp data structure coupling. Modules share a complex data structure and must understand its layout, like two chefs using the same complicated recipe format. Data coupling. Modules exchange simple data values, like passing a ball back and forth. Message coupling. Modules communicate only by sending messages or method calls without knowing internal details, like sending a postcard. Message coupling is the loosest and most desirable. Metrics turn the fuzzy ideas of cohesion and coupling into numbers we can measure. LCOM, lack of cohesion in methods, counts how many method pairs in a class do not share a common field. A common formula is LCOM equals 1 minus the sum over I equals 1 to m of the sum over j equals I plus 1 to m of share of I comma j, divided by m. Choose 2. Where m is the number of methods and share of I comma j is 1 if methods I and j use at least one same field, otherwise 0. Values close to 0 mean high cohesion, values near 1 mean low cohesion. Coupling factor CF measures the proportion of actual couplings between n modules compared to the maximum possible couplings, which is n times open parenthesis n minus 1 close parenthesis if every module could talk to every other. CF equals the sum over I equals 1 to n of the sum over j equals 1 to n, j not equal to I, of c sub ij, divided by n times open parenthesis n minus 1 close parenthesis. Where c sub ij is 1 if module I depends on module j, else 0. Smaller CF means looser coupling. Example, imagine 4 classes A, B, C, D. A uses B, B uses C, C uses D, D uses none. The adjacency matrix has 3 ones, so CF equals 3 divided by open parenthesis 4 times 3 close parenthesis equals 0.25, a fairly low coupling. These formulas help us see if a design needs refactoring. Graph theoretical modeling draws a picture of how modules talk to each other. Nodes, vertices represent modules, classes, packages, services. Edges, directed arrows represent a dependency. An arrow from X to Y means X calls something in Y. Dependency graph, like a city map where each building is a module and roads are the dependencies. If you can walk from one building to another, they are connected. Adjacency matrix, a table where rows are source modules and columns are target modules. Put a 1 in cell ij if module I depends on module j, otherwise 0. For the earlier example with A to B, B to C, C to D. Columns A, B, C, D, row A 0100, row B 0010, row C 0001, row D 0000. The matrix is easy for computers to analyze. Algorithms can count cycles, bad loops, find highly connected hubs, potential bottlenecks, or compute the coupling factor directly from the one counts. Visualization helps developers spot unexpected tight couplings, like a surprise shortcut road, and plan where to break them. Design principles give us recipes to keep cohesion high and coupling low. Single Responsibility Principle, SRP, a module should do only one thing, like a child's backpack that only holds school books, not soccer gear. This forces functional cohesion. Open-closed principle, modules should be open for extension but closed for modification. Think of a Lego set where you can add new pieces without drilling holes in the existing ones. Liskov substitution principle. Subclasses must be usable wherever the parent class is expected, like a toy car that can replace any other car without breaking the playset. Interface segregation principle. Do not force a module to implement big interfaces it does not need. Give it a small, focused interface, like giving a child only the crayons they will actually use. Dependency inversion principle. Higher-level modules should not depend on low-level concrete classes. Both should depend on abstractions interfaces. It is like two friends agreeing to talk through a translator rather than directly, making it easy to replace one friend. Design patterns that help. Facade provides a simple front door to a complex subsystem, reducing the number of dependencies a client sees. Observer lets modules listen for events without the subject knowing who is listening. Loose message coupling. Strategy swaps algorithms at runtime via a common interface, keeping the main class focused on its core job. Adapter translates one interface to another, allowing reuse of existing code without changing it. These patterns act like kitchen tools, mixers, knives that let you prepare many dishes without mixing the utensils for each one. When cohesion is high and coupling is low, the software becomes easier to take care of, test, and reuse. Maintainability. A highly cohesive module is like a tidy drawer. You know exactly where each item belongs. Changing one thing rarely forces you to open many other drawers. Loose coupling means you can replace a module, swap a broken toy without breaking the whole system. Testability. If a class does only one job and does not depend on many others, you can write a small test that checks its behavior in isolation, much like testing a single Lego piece rather than the whole castle. Reusability. A module with a single responsibility and clear interfaces can be taken and used in a different project, just as a set of cookie cutters can be reused for many recipes. Metrics back this up. Low LCOM and low coupling factor scores usually correlate with fewer bugs and faster bug fix cycles. Teams report that refactoring to improve these metrics reduces the time needed for new feature development by up to 30%. In the real world, we cannot always reach perfect cohesion and zero coupling. There are trade-offs. Performance versus decoupling. Direct method calls, tight coupling, are fast, while message-based communication, loose coupling, may add latency, like sending a letter versus speaking face-to-face. Legacy code. Old systems may have high coupling because they grew without design rules. Refactoring everything at once is risky. Teams often improve cohesion gradually, targeting the most problematic modules first. Team organization. When many developers work on the same module, tighter cohesion can cause bottlenecks. Too many people need the same room. Sometimes we split a cohesive module into smaller pieces to allow parallel work, increasing coupling a bit. Domain constraints. Some problems naturally need tight interaction, for example, a graphics engine where the renderer must know about the scene graph. Here we accept higher coupling, but try to isolate it within a well-defined layer. Balancing these factors is like balancing a seesaw. You push down on one side, more cohesion, and the other side rises, some coupling, aiming for a stable middle. Good architects continuously evaluate the cost-benefit of each change, using metrics and stakeholder input. Modern tools can automatically calculate cohesion and coupling numbers, saving developers from counting arrows by hand. Static analysis tools. Sonar Quibe, Code Climate, and Independ scan source code and report LCOM, coupling factor, and other metrics. They often highlight God classes, low cohesion, high coupling with a red badge. IDE plugins. IntelliJ IDEA's Dependency Analyzer, Visual Studio's Architecture Explorer, and Eclipse's Design Structure Matrix View draw dependency graphs and adjacency matrices directly inside the editor. Architecture Visualization. Tools like Structure 101, Archie, or GraphViz generate interactive graphs where you can click a node to see its inbound and outbound dependencies. Continuous integration. Metrics can be part of the build pipeline. If the coupling factor rises above a threshold, the build fails, prompting developers to refactor early. These tools turn abstract concepts into concrete numbers and pictures, making it easy for anyone, even a child learning to code, to see how clean or tangled their design is. By integrating them into daily work, teams keep cohesion high and coupling low without manual effort.